welcome back. And in this video, we will discuss the derivation of the ultimate moment capacity of a rectangular concrete beam. You're at work, your boss is asking you to calculate the ultimate moment capacity. You have two options: either use AI or maybe be like me and be traditional and go back to your textbooks. I'm a bit worried about our brains these days when we're using AI too much. So yeah, let's get straight into it. We have a beam with a length L and a uniform load of W star. Let's go back. Okay, now we know that the M star, the applied moment, is W L squared over 8. Please don't forget that. And we want to make sure that M star is less or equal to phi, which is that reduction factor, multiplied by the ultimate moment capacity, MU. We will just focus on this component today, MU. Okay, this beam is sagging, which means it's giving me a happy face. There is tension at the bottom and compression at the top of the beam. We have if we take a cross section of this beam, we have a full depth D, a constant width B, effective depth DST, which is the distance between the tensile reinforcement, the center of the tensile reinforcement to the compressive face of the concrete. We have a strain diagram with the maximum strain at the top of the concrete, and that's given to us depending on which code we are using. I'm using the Australian code, and that is 0.003, which is 0.3%. The tensile stress is at the steel level, not at the concrete level, because concrete doesn't take tension. All tensile is developed into the steel. Okay, and then we have a stress diagram. We have the width of the compressive block, which is alpha 2 FC dash, and the depth is gamma KU DST. We have a force here T, and the force is developed into the reinforcement. Two things you need to remember, and you will be very grateful for it. The first thing is force is equal to the stress multiplied by the area, and moment is equal to the force multiplied by the lever arm. And I think this is it. We can stop the video here, to be honest, because once you know these two things, you will know everything. Okay, now what do we need? Well, we have a compressive force at the top, okay, which is called C, and C acts at the center of the compression block. And then we have a force T, and T acts at the reinforcement level. Right, so that means, what is C? Let's see what C is. C is the stress, and I'll call it here alpha 2 FC dash. And I think many of you might ask, what is alpha 2? That is given to us, I think it's clause 8.1.3 in AS 3600. Please look up your own code around the world, but we are given alpha 2 is dependent on the compressive stress. For memory, it's 0.85 times, I think, 0.0015 FC dash. And alpha 2 has to be greater than 0.67, something like that. So yeah, let's continue with this. The compressive force is alpha 2 FC dash, that's the stress, multiplied by the area. What is the area? The area is gamma KU DST times B. Okay? And the tensile force in the steel is the yield stress. Again, we talk about stress multiplied by area. So stress multiplied by, what is the area? Is AST. When everything is all happy, we say everything is in equilibrium, which means that the compressive force is equal to the tensile force. And then we can say FSY, or do it that way, we'll say alpha 2 FC dash, okay, gamma KU DST times B is equal to FSY of steel. Let's call this 1, equation 1. And I'm reaching the end of the page. Alright. And then the second thing we need to know is the ultimate moment. Now, what is the ultimate moment? Mu is equal to the force, whether compression or tension, multiplied by the lever arm. Let's do this here. The lever arm is the distance between here and here. We can call this Z. And we remember that dst is the distance from the reinforcement to the top. That's called dst. Good. So mu is equal to the force, tension or compression, multiplied by dst minus half of the stress block, which is half gamma. Just remember here, this the distance between here and here is gamma ku dst. Half gamma ku dst. Right, I'll rewrite this clearly. Mu is equal to Fsy, let's take the tension, Fsy area of steel, multiplied by dst minus half gamma ku dst. Okay, we can then take dst common factor, therefore we can say Fsy area of steel, and then take dst common factor, then you'll have 1 minus half gamma ku, and that's it. Good. So we can call this 2, and I keep reaching the end of the page. Right, do we know gamma ku? We can figure it out, but we can also go back to equation 1, which is that one here, when we equated the compression and the tension together. So we can work out gamma ku from here, from equation 1. So from 1, gamma ku is equal to, what do we have? We have Fsy, area of steel, divided by alpha 2, Fc dash dst multiplied by B. So substitute gamma ku into equation 2. So then we say mu, the ultimate moment, is equal to, let's go back to equation 2. We have Fsy, area of steel, dst, open a bracket, 1 minus half, and what is gamma ku? Actually, we might even call this equation 3, so we can be pretty consistent. Half Fsy, area of steel, divided by alpha 2 Fc dash dst times B. Close the bracket. And that's it. That's the derivation. This is as simple as that. We know that Fsy is the yielding stress of the steel, which is given to us probably at 500 MPa. Area of steel is you're given that from the equation, or from the problem, whatever it might be. dst, you know what that is. So we know all these parameters. We know what dst is, and we know what alpha 2 is. I think alpha 2, if you go back to clause, I'll look it up. It's 8.1, here it is, 8.1.3, and that is 0.85 minus 0.0015 Fc dash. Okay, and alpha 2 has to be greater or equal to 0.67. Can't memorize that, but I have to go back to my textbooks. Okay, so this is, and this is from AS 3600 2018. So it's yeah, so alpha 2 is dependent on Fc dash. And yeah, and also if you want to know what gamma is also in the same clause as alpha 2. Gamma is simply 0.97 minus 0.0015 0025 FC dash, and gamma has to be greater than greater or equal to 2.67. Okay. We can, if you're using, say, FC dash as 20 MPa for argument's sake, right? Then we can use a rule of thumb using the ultimate moment, and let's assume the Ku value, which is the ductility, is at maximum of 0.36. Okay. Anything more than 0.36 just means that the beam is overly reinforced. In an over-reinforced beam, the compressive force in the concrete would reach the limit before the steel yields. So in cases like these, we could just get a non-ductile sudden beam failure. So if we assume 0.36 and we work out gamma, given FC dash is 20 MPa, mu is going to approximately be, so I should use this, approximately, about 0.85, say, right? FSY, area of steel, times DST. It's about 0.85 times DST. Yeah, so this is just a quick formula instead of using that big formula that we worked out before. Worked out here. Right over here. Okay, so what did we learn from all of this? I think that two things. Compression or tension are forces. And forces is equal to stress times area. And the other thing we learned was the ultimate moment, mu. And mu is a force multiplied by the lever arm Z. And that's it. Hope you enjoyed this. Share, like, subscribe, and have a great afternoon.